My topic of discussion is Go and gRPC best practices to build a bus recommendation engine. The idea is to efficiently program your microservices in a way that they are highly maintainable and scalable, and have a better communication between microservices. To give you an overview of how bus search works, is basically you search for a source city or a boarding point in the city, and a destination city or a dropping point in the destination city for a particular date of journey. And you get a list of services which you can opt from. Here in this talk, we will discuss about algorithm called learn to rank. The basic idea is if you can capture the last 6 to 7 hours of user interactions and last 3 to 10 days of transactions done, and multiple bus features that we already have for from our inventory, if we can utilize all of them and somehow better rank our inventory. So because most of the transactions are happening in top of the inventory, so we want to use this data to better rank our inventory. So look at the high level flow. Whenever a user makes a search on Redbus, the request lands to a search service, and search service fetch the data from inventory service, and it send the data to a ranking service gRPC to rank the inventory. And basically, to facilitate learn to rank, we have created a feedback loop where all the user interactions, viewing a particular service, clicking on the seat layout, all your available seats at the moment of search, all this data are pushed to a Kafka topic, and a Kafka consumer is aggregating this particular information in our Redis cluster in a required format. And ranking service, what it does is it fetch all these dynamic parameters from Redis cluster in real time, and all the inventory information from search, what it has received, it pulls a machine learning model from S3 and cache the model object in memory. And it predicts the rank and send the response to the search service. Whatever is the input to the model and output to the model is pushed to another Kafka topic, which is further consumed and aggregated in a Redshift, so it can be further analyzed. To look at the main responsibility of ranking service here is there are like around 30-40 algorithms which we need, which might vary based on the user, geography, or what kind of channel you are using, either Android, iOS app, or web application. Or a shorter route or a longer route might have different algorithm. So we wanted to have a service which has the configurable way of lots of algorithms. And based on the context, it can fetch a list of algorithms which are applicable in a certain priority order. Each algorithm is implementing only just 2 methods, whether algorithm is applicable or not, and what's the algorithm. So it fetch all the eligible algorithms in a chain of responsibility manner, and then returns the final ranking results to the search service. One such algorithm is learn to rank, which is basically all the static parameters in learn to rank are powered by the inventory service, and all the dynamic parameters are from a time series database, which we are using Redis as time series database. And for each service, we are preparing size of 28 feature parameters, and this 28 into number of services, this matrix we are feeding to a regression model, which is finally predicting the rank for us. To look at the model, what kind of model we are using gradient boosting regression trees. Gradient boosting regression trees are composed of your decision trees. In decision trees, all your nodes are decision nodes, which either splits a set or take some decisions, and all your leaf nodes are classification nodes, which decides. Let's say if you are classifying something like cat, dog, horse, or cow, your labels might be 0, 1, 2, 3. Okay, so there are 2 kinds of decision trees: classification trees, which takes a discrete set of values, and regression trees, which takes continuous set of values like real numbers. In our case, they are predicting a score which might be from 0 to 1. These gradient boosting regression trees are composed of multiple decision trees. So if you are seeing here gx equal to f0x, f1x, f2x, your fx are decision trees. And there are two ways to build regression trees. One is gradient boosting, in which you build decision trees step by step. So you have a base decision tree. On your training data, you train that decision tree, and then you check in your training data, you check with the actual output, what's the residual. And then you train your second decision tree, and you keep on doing that till you get a desired result. There is another way to prepare regression trees, which is random forest, where you train multiple decision trees in parallel and then combine them together to get a desired result. Here we are using gradient boosting regression trees, which are giving us the efficient results. And we are using LightGBM Golang library, which is pretty fast to facilitate to inference the model. Now, since we are aware of the model, let's have a look at the data aggregation part. Redis as time series database. So we tried standard time series database like InfluxDB, and since it's not an in-memory solution, it was to fetch multiple parameters for n number of services. It was taking around 100 to 150 milliseconds. And we want our search to be served in 100 milliseconds. So just getting the data for a ranking service, 100 milliseconds is not feasible. We needed a solution which takes less than 5 milliseconds. And Redis served us well. It was taking 2 to 3 milliseconds for all the parameters for all the services. And so what are Redis sorted sets and how we store the data in it? So like in Redis support multiple data structures like hash set, normal, key value pairs. So instead of having normal get set commands or h get set commands, here in Redis sorted set you have z star commands. And the data is like a ordered hash map. The data is not sorted with respect to your keys. Like in an ordered hash map, your data is stored with respect to keys. Here you have, for a particular key, you have multiple values. And in each value, you have an element and a score. So the data is, these elements are sorted with respect to the score, and you can do range queries efficiently. So here, like one z star command is z count. Given a range of score, here I'm giving minus infinity to infinity to minus infinity to plus infinity to get all the elements, but you can give a start score and end score based on what kind of data you want to get. Here my key is composed of a service ID and date of journey and view count I'm looking at. There are multiple features for which we are using Redis sorted sets, and your element is a unique session ID because we needed unique counts. And your score is a time, so I can query for last 1 hour data, 3 hour data, 6 hour data, and get the momentum of this data to finally put this data in our regression model. How we are querying this data from Redis is basically, in Golang, we are creating this script. This is a Lua script, which you can directly run on Redis and do complex operations. So here I have a list of services for which argument 1 and argument 2 is your start time and your end time. And you are preparing, basically for available seats, I just need a footprint of like what was the data before 6 hours. So first footprint is good enough for me. So I'm just passing a limit of 1. I'm aggregating the results in an array, and then I'm returning that. So these Lua scripts are pretty efficient, so you don't have to make calls from your server to Redis back and forth. You can do everything in the one Lua script, and it gets executed very fast. To fetch multiple such parameters, we have around 12 parameters. So if we do it sequentially, it was taking 20 milliseconds. But what we have created is for each feature, we have created a map, feature key as some string, and value as a function which returns the index where the value needs to be stored, like 0 in this case, and how to fetch that value, like find available seats. And then we have all these 12 parameters in a map, and we loop through the map and run 12 parallel Go routines to fetch this data, and the data is stored in a data list where each index is independent, so data is stored independently, and once all the Go routines are done, your data fetching part is done efficiently. So now we have designed all our components of our microservice efficiently. Now let's look at the communication part. So for communication, we are using gRPC. Basically, gRPC stands for general purpose remote procedure calls. The idea of remote procedure calls comes from 1970s, where you call a remote procedure, remote method, as if it is present on your local system. And Google took this idea, and in 2000, for the internal microservice communication, there was a project called Stubby, where they were already using this for the internal microservice communication from 2001. And in 2012, so gRPC is utilizing two frameworks, which is HTTP2 and protocol buffers. In 2012, around, there was a project called Speedy, which was being tested on Firefox, and it later got standardized into HTTP2. What made HTTP2 stand out in its performance is its binary framing, where in HTTP1 there was a ASCII encoding. It's multiplexing. So if you are sending thousands of requests in parallel, you can, in a single packet, you can multiplex multiple requests and responses while getting back. And header compression. So HPEC, basically, you have a lot of static headers, okay? So some of the headers are just static, like content type, JSON or something like that. These, based on how common the header is used, they can be compressed to a single byte. Let's say most commonly used two headers will become compressed to 1 bit, second will be 2 bits, like this, and like a Hoffman compression algorithm. So in 2012, HTTP got released, and so in 2015, Google utilized this HTTP2 and protocol buffers, and they made gRPC open source. Protocol buffers are basically an interface definition language, which is to basically you can have a common contract for your microservices, and you can generate the you can use Protoc software to generate code in any language for to run it in any platform. So you have a common contract, and the same contract can be used on your client, and same it will generate the bindings for your client and server, and that can be used by your. It has an efficient way of runtime libraries to serialize and deserialize your code. And it's platform neutral and language agnostic. Your server can be in C++, your clients can be in Ruby, Go, Java, anything. To have a look at the real-time example of our ranking service, we have a remote procedure call exposed like rank inventory data, which takes, so you register all your RPCs in your service definition, which takes a ranking request, which has a list of inventory information and a serialized base context. Further complex object can be defined in the protofile itself with their detailed definitions. And we are returning a response of the final order in which the inventory needs to be shown. So here map, only a list you define using repeated, otherwise the syntax is pretty simple for protofiles. How do you start a server? So you you create a listener on a particular port. You define based on your requirement, whether it's a unary interceptor or stream interceptor. For our purpose, we needed just sequential communication, that you send some data and then you get a response to order your inventory. So we are defining a unary interceptor. Then you register your controllers, and all your methods will be registered, and then you start listening on a particular port. We are just using application monitoring middleware, but you can also have logging, monitoring, and authentication middlewares while you are defining your gRPC server. gRPC, it also support, apart from unary interceptor, it also supports server-side streaming, client-side streaming, or bidirectional streaming. And your controllers, whatever the generated bindings from your protofile are accessible like your interfaces, and you can access the request and response and do whatever processing you wanted to do. Here in our case, we are just deserializing the context that we got, and we are sending the request to a ranking handler, which will further opt for the algorithms that needs to be run and then execute them. At the client side in Java, we are based on your gRPC URL. You will create a managed channel. Based on your HTTP or HTTPS, you will use plain text or transport security. You can have any load balancing algorithms configurable. You can enable retry, and everything in gRPC is mostly plug and play. So you can opt for any DNS discovery algorithm as well. And all these configurations you can also provide in a default config, and you create a channel. Here we were facing some scaling issues, so we created a pool of channels, and we were picking a random channel from the pool, and then we are creating a blocking stub. So in case you need you need to do a sequential execution where you send a request and get back a response, you will create a blocking stub. If you want to do a asynchronous operation, you will create a non-blocking stub. We are defining inbound and outbound message sizes to optimally do our multiplexing. And then you call rank inventory data method as if it's present on your local system. This is the gRPC policy that I'm using for my service. So we were getting some failures for service unavailable cases. So I have defined a retry policy with maximum 5 attempts. You can configure your initial backoff time and max backoff time based on the response time of your service. And also, like all the configurations regarding round robin, load balancing and all, you can do it here. And you can pass this configuration while creating a channel. So when we released this service, we were getting 1 to 2% failures, and we tried multiple solutions. To start with, we created a pool of 20 channels. We changed the pool size as well. We passed a configuration file with retry mechanism. To start with, we were using classic load balancers, but then we took a AWS gRPC supported load balancer, so you don't have to, a standard classic load balancer might be just supporting HTTP1, and intermediate requests will be converted, and there might be lots of complications. So we added this gRPC supported application load balancer. We defined the retry policy, and for service unavailable cases, we were getting this. So with these solutions, we were able to resolve our 1% failures. And our service, when we launched, it was efficiently giving our results in 200, 300 microseconds. When we released more complex algorithms like LTR, which were taking around 4 milliseconds, the response time got increased to 0.8 milliseconds. But the idea here is, if you efficiently design each component of your microservice and then make them communicate efficiently, you can come up with such efficient services. And also, like using some very basic patterns, you can come up with a very maintainable solution. So in our case, if you just need to add a new algorithm, you have to just write 2 methods and plug and play, everything will start working. So that's all, guys. Thank you. Any questions?
Questions, please. Yeah, keep your hands raised so that we can follow up.
Hi, I'm Ayush from Pamatic. So I think at the start you showed like for a ranking algorithm, you take inputs. Based on the input, you decide on which algorithm to use. So for deciding, let's say there are 2 algorithms which comes out, like you need to use that. So for that also you use ranking. Do you apply a ML model to it? And on a follow-up to that I have is like, before applying even a ML model, did you try with, let's say, rule-based ranking? Was it too complex? it didn't work out. So yeah.
So based on the context, mostly the priority order of those algorithms is configurable. Certain geographies might, let's say, 4 algorithms running in certain priority order. Certain geographies and certain source and destination might have just another 3 algorithms. And then we further check, like, out of those 4 algorithms which are eligible for this particular request based on a lot of parameters. And then we just execute those requests in that particular order. And once we get the desired result, we come out of that, sir.
Okay, and like, did you just go with the ML based algorithm, or before going with ML based? Like,
so there are lots of algorithms which might not be ML based. There might be a static mathematical model which is boosting some services up based on your offers. There might be a lot of other parameters based algorithms which are not machine learning models. Here learn to rank was a machine learning model where we were using a regression model, but they don't have to be machine learning
Yeah,
models.
my question was more like, from the start you started using the regression model, or you tried with maybe a rule based ranking, it didn't work out. Just wanted to understand that, because that is something
to
which-
start with, like, there were a lot of algorithms which were not machine learning algorithms.
Okay,
This
okay.
we recently implemented like around a year back, and then we got good results. So yeah.
Okay, thank you.
I think there's a question at the back. There.
Yeah, so my name is Vaishak. I'm working out of a company called Keyvalue in Kerala. So what I have is actually a two-part question. So I saw that you guys were switching from influx to Redis sorted sets for the time series DB. And one I want to know was, did you try benchmarking any other time series DBs like Prometheus or Victoria Metrics, for instance? And the other one is how, like, is there any possibility to...
I think you want to ask one question at a time.
Yeah, it's the same continuation question because... Okay, yeah.
Take one small question at a time.
Yeah.
Evaluation of time series databases, is that what your question was?
Yeah. Because essentially, is there any other benefit than speed for using Redis sorted sets?
So for time series databases, like, we tried InfluxDB, and there might be other solutions, but as long as they are not in-memory solutions, they might take up to like 30-40 milliseconds. And our requirement was under 5 milliseconds. So a caching kind of a solution was pretty obvious. But then we got this sorted sets option, which fulfilled our requirement. Yeah.
Oh, so yeah, okay. So it's in memory, and that's why it's suiting your
It's
use.
fast. So
Yeah.
for every key, you will get the data in order 1, and you will do the range queries in your number of elements in log and time.
So yeah, the other part, like, is it possible to visualize this in Grafana or something? Because we had the same problem, and we were switching from Influx to Victoria because we wanted to visualize this data and monitor it in real time.
Grafana I have personally not used, so I will not like to comment on that.
Yeah. Okay. Yeah, catch it later.
You might want to evaluate things like timescale.
Yeah. Basically, that's what I was thinking. Like, because if it is possible to see this in real time, like, I'm not really familiar with Redis sorted sets.
Yes,
Yeah.
maybe we can discuss later and discuss your
sure.
problem as well. Yeah.
Right, more questions.
Yeah, hi Pawan, I'm Atharva from Pomatic. So like I had one question regarding your ranking algorithm. So you mentioned like you choose a light GBM over rainforest, and because of some efficiency reasons you choose that. So like, can you elaborate more on that point? Like what were the efficient, like in terms of, we are speaking about speed, or was it the accuracy, or what is it?
So why we have used light GBM over what?
Random forest you mentioned in your slide, right?
Over
Random forest.
random forest.
Yeah.
These are just two different algorithms to basically do a regression in your decision trees. Your linear regression is a curve fitting kind of thing, right? Where you define you train your polynomial function and then do the prediction. In decision trees, there are only two ways to do regression. One is random forest and one is gradient boosting. Gradient boosting comes up with a lot of advantages when you are doing a step-by-step thing, right? You are in a gradient. It is basically the idea is coming from your gradient descent. Like, you go to a random point and then you try to minimize the loss till you go to a local minima, right? That instead of having a random forest where multiple decision trees are trained independently and predict the score, this was more intuitive to us, and also it was giving us a better efficiency, like in terms of our ranking.
Okay, thanks.
All right, some more questions. There's one here.
Hey, I'm Agni from Funnel Story. And so for your ML model, what kind of training data did you use and how did you generate that?
So like whenever a user search, we push lot of these data into our data lake, okay? And we use the same data in Redshift. We are storing this data. So same data set we use to train our models.
One question here.
Okay. In 2 to 3 places in your talk here, you mentioned this strategy or this algorithm worked better for you, right? So my question is, what evidence, proof, or tests did you have to support this assertion that this algorithm actually generating more relevant results?
So basically, like the way we have done the comparison is we try to run a AV where your 50% traffic might be running on some old algorithms which we were using, and 50% traffic is running with this new algorithm. And then we try to see where was the conversion rate more. So we just try to compare the CR.
I see. So the tests were not based on the relevance or the performance of the algorithm, but of the product resulting.
Ultimately, it comes down to how it's performing on business logic, like how it is giving you more money.
All right. Thanks.
And one last question here. Is there any other how many people have a question still? All right, one last question.
Hi, I'm Aditya working at SAP Labs. I have a question. When you said that to search in those 12 parameters, you used the sequential and you got around 30-40 milliseconds times, and then after you use that maps thing and redis sort to reduce the time, right? So what other methods you went through, or maybe what results you get at? I mean, you directly did not get to that method, right?
So when you are doing a sequential execution, even though sequential parallel execution was not so intuitive because your Redis is a single-threaded application, so doing a parallel execution might not help. But we compared, like whenever you are doing concurrency, try to benchmark with a normal solution with a parallel execution solution and try to see whether which algorithm is taking what kind of time. So what happens is when you are making like 10 parallel requests to Redis, sequential execution might, let's say one execution is taking 1 millisecond to go to network, 1 millisecond to get back, 0.1 millisecond to execute on Redis, so it's 2.1 millisecond for one request, so it will take 21 millisecond for 10 parameter fetch, right? But when you are doing parallel, all those at least the network calls can be parallelized, right? So now in 1 millisecond, all your requests are on Redis. Now it might take 0.1 millisecond for 10 and it might take 1 millisecond for the entire execution. And in 1 millisecond, you get back your answer. So it will come down to 1 millisecond for execution, and 3 milliseconds, right? So that was the idea. We also compared it with the sequential execution and we found it more helpful.
Okay, thank you.
Nice. Thank you so much, Pawan. Loud round of applause for him, please.
Thank you, everyone.